Our next lecture, the next weapon in the crypto arms race, asymmetric key cryptography, aka public key. As we know from the last lesson, symmetric key cryptography uses the same key for both encryption and decryption. And we also know that the key must be kept secret between the communicating parties. Because the key must be kept secret, it is called private key cryptography. The major challenge with symmetric or private key cryptography is secure key distribution. If the key is intercepted or compromised during exchange, the entire security of the communication is compromised. In response to these challenges, asymmetric encryption was developed. Asymmetric key cryptography was introduced in 1976 with the groundbreaking Diffie-Hellman key exchange, which allowed two parties to securely exchange cryptographic keys over a public channel. Asymmetric key cryptography offers a solution by enabling secure communication, as long as the parties can trust the integrity of the public and private keys. While symmetric key is known as private key cryptography, asymmetric encryption is known as public key cryptography. Where symmetric key cryptography uses a single private key, public key cryptography uses a pair of keys. The term asymmetric highlights the fundamental difference in how the two keys are used, one for encryption, one for decryption. The two keys are mathematically linked, so that information encrypted with one public key can only be decrypted with the mathematically linked private key. Unlike symmetric encryption, where a single key is used, asymmetric encryption relies on the mathematical properties of prime numbers to generate secure public-private key pairs. Each entity, whether it's a user, system, organization, typically has a key pair consisting of a public key. This key is shared openly and is used by others to encrypt messages or verify digital signatures. And a private key. This key is kept secret and is used to decrypt messages or create digital signatures. For example, if I wanted to send an encrypted message to you using public key encryption, which is asymmetric cryptography, I should follow these steps, right? I want to encrypt the message, so I use your public key to encrypt the message. Your public key is openly available, so anyone can use it to encrypt messages for you. However, since it's encrypted with your public key, only you can decrypt it. Then we have to decrypt the message. When you receive the encrypted message, you use your private key to decrypt it. Your private key is secret and only you should have access to it, ensuring that only you can read the message. So in summary, encryption uses the recipient's public key. Decryption uses the recipient's private key. This ensures confidentiality as only the intended recipient, me, can decrypt and read the message. So we're going to have you practice this concept. In the example above that just talked to you about a second ago, I am the sender and you are the receiver. Now think about Alice being the sender and Bob being the receiver, and fill in the blanks below. So you'll see this says Bob is receiving a message from Alice encrypted with public key cryptography. In order for Bob to receive it securely, it must be encrypted with a name, okay? And is that public or private key? Once Bob gets the encrypted message, he can decrypt it using a name, put in the name, Alice or Bob, and public or private key. So we'll give you a few seconds to take a look at this and come up with an answer. What do you think it is? There we go. So you'll see that in order for Bob to receive it securely, it must be encrypted with Bob's public key. Once Bob gets the encrypted message, he can decrypt it using Bob's private key. So you see, only the person receiving the message needs to protect their private key. Other people can use public keys to send secure messages, but they don't need to know or access the private key. This makes public key cryptography particularly useful for secure communication over an open channel. Hey, like the internet, where it's unsafe to share symmetric key directly. This ensures confidentiality as the only intended recipient, which would be me in the case we talked about, can decrypt and read the message. So there are some key advantages to asymmetric key encryption. It does solve the key distribution problem. There's no need to securely share a secret key in advance. It's scalable, and it enables digital signatures, which you'll learn about later. It can prove authenticity and non-repudiation. There are some fairly common asymmetric algorithms. RSA, which is based on factoring large prime numbers, huge. The ECC, which is smaller key sizes for equivalent security, and Diffie-Hellman, which is a key exchange protocol. Now, when we're comparing the two, if we look at the keys, in a symmetric, there's one key shared. Asymmetric, you have your key pair, the public key and the private key. The symmetric is usually a bit faster than asymmetric key encryption. It is a little bit slower because it is computationally intensive. The key distribution for symmetric key is challenging. Asymmetric does solve that public key approach. And strength, symmetric is strong with sufficient key length. Asymmetric key cryptography is strong based on mathematical problems. There are some practical applications. Secure web browsing, HTTPS, you'll see that. Secure email, digital signatures, which we'll speak about later. Virtual private networks, so VPNs, use asymmetric key cryptography, and cryptocurrency transactions. Most real-world systems use both asymmetric and symmetric. So they use symmetric encryption to securely exchange a symmetric key. We use the symmetric key for bulk data encryption. And so an example of that would be like TLS handshakes in HTTP. Some of the key takeaways from this lecture are that asymmetric encryption solves the key distribution problem. We have key pairs. It uses mathematically linked key pairs instead of a single key. Public keys can be freely distributed and shared. Private keys must be kept secure, and they're used to decrypt messages. This forms the foundation of modern secure communications. Some of the questions we might want to consider after this lecture and learning this material is: how has asymmetric encryption changed the digital landscape? What mathematical problems underpin the security of public key systems? And then how might quantum computing affect asymmetric cryptography? Interesting. So the next steps, you're going to learn about digital signatures, authentication, public key infrastructure, certificate authorities, and modern applications in web security. So on our last slide, we do have a few additional resources that I hope you take a look at and enjoy. Well, thank you.